I'm Lim Jihang, I'm from Group 2. We are going to design an FIR and IIR filter to remove noise from the audio signal. The first step is a sampling process. First, we read the audio signal, which is in continuous time. Then, for ease of analysis, we convert it to discrete signal by sampling. For the plot, we can see that we convert the time domain to discrete sample, which is represented by square bracket n with sampling frequency of 8,000 Hz.
Moving forward to the discrete time Fourier transform (DTFT), sampling does not have much meaning to filter analysis. The DTFT is crucial for converting a discrete time domain signal into frequency domain, enabling the exact noise frequency to be identified and filtered. The fast Fourier transform is then used to plot the frequency spectrum, which shown at abnormal spike at exactly 800 Hz, the target frequency to be removed. However, a single FFT is not enough, so we use a spectrogram to show the direction of noise across the entire audio file. From the graph, you can see a solid red line at exactly 800 Hz, indicating the noise is constantly across the whole track, making a notch filter ideal.
The DTFT analysis and sampling part, we know that our sample rate is 8K Hz here, and we know that our target noise is 800 Hz. And however, because the target noise is set at 800 Hz, we need to establish a bandstop region and around plus minus 25 Hz. So our lower and upper frequency is curve frequency is 775 and 825 Hz. And here we actually found the order from the variable we type, which is the rectangular Henning-Hamming diamond, and the method already taught by our lecturer. This is a 144, 496, 548, and 888. And actually, we will choose the Hamming because it offers the optimal balance. It gives a moderate manageable filter order while it's still providing excellent stopback attenuation, which is negative 46.28 decibel. And this is the impulse response that we found from the manual calculation. This is the plot. And actually, for FIR impulse response, we actually got a MATLAB code function, which is FIR1. And the default mode is actually a Hamming window, so we don't need to change anything to create the plot. And for the phase response, we can see it's actually linear, and it guarantees zero phase distortion, properly preserving the original waveform without delay or something. Next to the linear transformation. Okay, so linear transformation, same as FIR window method, we need to find the order of the Butterworth one stop first before we determine the coefficient. And this is the order we found, which is second order, and same for the low pass filter, when you use the table, and this is the table formula. But however, the critical part is we need to change our S to become the PS over S square minus omega naught square. And this is the HS we found. Here, the difference equation coefficient that we need to pass to the zero analysis. And the alternative method using MATLAB is actually using this butter function. It's actually get the same moderate same result. You can see 0.9723 and this is 0.9726. It's actually more likely the same. And this is the IIR phase response. But unlike FIR's design, the IIR filter will exhibit a highly non-linear phase response because it's used a very low order filter, but it creates a highly efficiency. So that's all for me. Now I'll pass through to whoever. Thank you.
My name is Yufan, and now I will continue to present the next important part, which is the G-transform and the G-plane analysis. The step is important in the filter design process to verify and ensure the design filter is stable and physically realizable. First, let's discuss for the FIR filter case. We can convert the impulse response of the Hn that get from the previous filter design process and convert it into the G domain, which is a capital Hz. Since our filter order n is equal to 528, therefore we will get a 528 order polynomial for numerator, which is a 0. They're expected to be distributed around the unit circle and 528 poles at the origin. Next, to visualize the G-plane plotting, we need to utilize the function G-plane, where B is the filter input coefficient and A is the filter output coefficient. And we will obtain such plotting result from the FIR Hamming filter with 528 filter order. Observe from the plot, since all the poles are located at the origin, therefore the RLC will be Z greater than 0. Next, we will check for the stability. Since the RLC region covered the unit circle, therefore the filter was considered stable, and again FIR filter will always be stable. For the causality checking, since the RLC region is right-handed, therefore the filter is causal and physically realizable. And for the filter characteristic, since our target noise to be removed is at 800 Hz, therefore from the frequency to angle mapping calculation, we get that the noise is located around the 36 degree at the unit circle. And cluster of 0 will be placed at there, and also its conjugate negative 36 degree to attenuate the noise. Now, let's discuss about the IIR filter. The state is almost similar with the FIR. For the RLC region, the difference is that we need to choose the poles with the most greater radial distance from the origin. And for stability, if all the poles lie inside unit circle, then the filter will be considered stable. In this case, yes, it is. Causality checking. Since RLC region also right-handed, therefore the system is considered causal. For the filter characteristic, same, there will be zeros placed exactly at plus minus 36 degree, which corresponding to the noise. The difference with the FIR filter is that the G-plane of the IIR filter doesn't have a dense rings of 0 around it. And that's all for the G-plane analysis. Thank you.
Thank you, Ivan. So I'm going to continue with the conclusion part for our filter design. The first one is the FIR filter. which FIR is actually already a finite impulse response, so we can directly apply the convolution function by simply computing the output by taking a weighted sum of the current and pulse input samples. So this way is actually like just inverting the filter function Hn and then multiply by our input signal. The next is the convolution for our IIR filter. Since IIR is an infinite impulse response, we cannot directly apply the convolution function. Instead, we need to use the filter function, which is actually a recursive convolution, by computing the output by combining current and pulse input samples with the feedback loop of pulse output samples. So this is the example for our IIR filter convolution, and this is the example for our FIR filter convolution. And then by plotting the output graph, we obtain this final filter function graph, which this is the Hamming window filter function, and this is the IIR filter function by using bilinear method. And this is our final filter output signal, which the first one is original noisy signal, and the audio listen like this.
0125.
Next is the filter output signal through Hamming window, and the audio listen like this.
0125.
The last one is the filter output signal through IIR filter, and the audio listen like this.
0125.
So thank you, and that's all from us.